All right, we have our Spring Pendulum Jupyter notebook. I would like to play around with these initial conditions a bit. So here I ended up with a scenario where the fundamental frequency of the pendulum is much smaller than the fundamental frequency of the spring. So let's think about this. For instead of frequency, let's think of it in terms of period. Yeah. So for the period for the pendulum, this is 1 over 2 pi square root L over G. Is that right? Excuse me. That's actually 2 pi over here. That's right. 2 pi square root L over G. There we go. Okay, and for a spring, I know for a spring that its angular frequency is root K over M. I swear that's a K. So this thing is 2 pi over T. Right, T for the spring. So that means T for the spring is going to be, take this, move it over to the left-hand side. That's what I did here. Take this, move it over here. So that leaves me with a 2 pi, because the 2 pi doesn't go anywhere. Root M over K. All right, cool. So I have the case where TP is much bigger than TS. How did I end up with that? TP much bigger than TS. I end up with that because, because my K is rather enormous, right? My K is 100, so I've got 100 down here in the denominator and not a very big mass in the numerator. So that gives me a very short period here. And then for my T pendulum, I have root L, and L is a middle-ish number 1, right? There's nothing more moderate than 1 in math. And a G of 0.5, so that increases by a factor of 2, and then that gets square rooted, so it increases by a factor of 40%. So my TP is kind of a normalish number, and then my TS is kind of a rather big number. So why don't we try decreasing the K? I suppose the simplest state would be to keep everybody at 1, right? So my L0 at 1, my G at 1, my K at 1, and my mass at 1. Now, it's important to keep in mind, these things are not necessarily constant, right? The T for the spring is constant, because this is 2 pi root M over K. And those two things are not changing. For the pendulum, though, this L is changing. And so I'm kind of using the L0 as an average value there. So let's call this thing an approximate and put a 0 on that, because in principle, every time that L changes, the period for the pendulum changes too. However, it's constantly changing, right? It's always, going in, it's always getting longer and shorter there. So I suppose it's okay to replace it with an L0 because it all kind of averages out. So let's try this. Let's try them on order with each other. Close this diagram here. Oh yeah, I recently discovered that there's a little green arrow that follows along here on what line the code is most recently on. It doesn't always track. Like there it is, and there it is, and like I don't see it going. Like it'll skip over the stuff that doesn't take very long, but then it's like sometimes sticks here on. I guess the idea is that if you're in Python, you're supposed to always be calling functions, and so it'll hover over there while you're calling a function that does a thing. Let's see, I have my graphs. Why is it taking so long here? Okay, cool. Yeah, there's my issue with my conservation of energy there. I might need to go back and hopefully someone by now has posted a comment for what I did wrong there. But anyway, here things get very different because let's start with the trajectory. So the trajectory, pretty straightforward, right? It almost looks like kind of a regular pendulum. And I think part of that is we've forced it to have the same period for both, right? Because we made everybody 1. All those 2 periods come out to be the same. So it is oscillating shorter and longer with the same period that it oscillates back and forth. Now, but the other thing to keep in mind is that that equation for a pendulum is already an approximation, right? Because a pendulum is not actually simple harmonic motion. Spring is definitely simple harmonic motion, but a pendulum is not, right? Especially for if we go to large angles. All right, so my theta is definitely looking strange here, right? That's definitely looking different than we had before. This is no longer, two sine waves on top of each other. Same thing here for the theta dot. That's interesting. We need to let this run for longer. L, on the other hand, is moving along very nicely. The pendulum seems to care much more about the spring than the spring does about the pendulum, although we do get a little kink here for the L dot versus time. Okay, yeah, energy's behaving interestingly there. Why don't we have this run for longer? Let's have this go, let's go all the way to 100. How about that? Your session crashed. Oh, I used all available RAM, did I? Okay. Okay, so ran into a little issue. My session crashed after using all available RAM. If I'm going to get Colab Pro, I'm going to need some additional help on Patreon. So here's what we'll do. We're just going to have why don't we have every 100th data point recorded? Yeah, let's do it that way. So we're going to do counter equals, data counter equals 0. I'm going to do data counter plus equals 1. And then if data counter equals 100, so do every 100 data points, only then will we add it to the lists. And we will reset our data counter. Data counter equals 0. Okay, how about that? Okay, so with that slight change, now we've got our graphs. We've got theta versus time. Very much not a sine wave anymore. Hardly even a modified sine wave. So it looks like it's like the wiggles have lined up with it, right? And so the theta dot is doing all sorts of interesting stuff because we have these changes in the concavity as we go around there, which is kind of cool. Let's see, for L, it actually ends up working out nicely. I mean, it still looks more or less like a sine or cosine. There's that trajectory we had earlier, and then our energy, yeah, definitely need to fix that, total energy there. Okay, so we've done a case where the spring was much faster than the pendulum. Can I make a case where the pendulum is much faster than the spring? So pendulum goes like root L over G. So if I make G large, let me make this 100. If I make G large, then that becomes a very small period, right? And so it should be swinging faster than it oscillates in and out. All right, there's our data. So we will get our graphs up now. Oh my, okay. So this just got interesting. Oh, look what happened to that theta. That's going all the way up to 1.5. So that's going up to pi over 2 and going down almost to negative pi over 2. Okay, so this thing is ending up at about a right angle. It's not going all the way over itself, I don't think. Theta dot, okay, yeah, those peaks in theta dot, that tells me I might need a smaller time step. Here is our trajectory. So this is with it swinging back and forth more quickly than it oscillates in and out. Really cool stuff there. Yeah, conservation of energy is a mess. We should probably just ignore, but it's following the right general trend there. Okay, that's really interesting. This is the most interesting trajectory I've seen so far. Okay, let's try this one more time. I'm going to give it more energy at the beginning. Let's have it start out at a higher theta. So this is theta equals 0. This is pi over 2, so about 1.5. So if I put it past 1.5, let's put it at, let's go all the way to 2. Yeah, see what happens here. Okay, very similar stuff. So you could probably classify a lot of these based on the general shape of the graph that you get. So like these things having so many sharp turns like that is a different feature than we had before. L is still you know, oscillating on its own, basically. All right, and this thing has become very interesting. That's an interesting happening there, because we start out... Don't we start out here? Okay, so we got 0, 0. Oh, no, I guess we start out somewhere over here. No, we should start out... We should start out above 0, shouldn't we? Should I not start out... Should I not start out above 0? From theta equals 2, and I come... Which way is positive theta? Theta's going to rotate. Oh no, theta positive is going to rotate this way. So I'm going to start over here. Seems like that should be getting above 0 somewhere, right? Because if my x starts out as L sine theta. Oh no, that's going to rotate. That's going to be over to the right. Right. Okay, yeah, it's going to rotate this way. And so my y list is negative L list cosine theta. So my cosine of 2 should be a negative number. So my y should be starting out as positive. Okay, maybe this is a sign that I do have something mistaken besides that, is that my y is not starting out as a... Maybe it is starting out as positive, and it's just barely above the 0. Oh, that's interesting. I'm a little bit concerned at how large these... Oh, I guess it's because the gravity is stretching it out so much, because the gravity is so strong it's getting stretched out down. Okay, yeah, I might be able to convince myself that that's above just a little bit. Why don't we take this thing here... where do I plot the trajectory? I plot the trajectory right here. Let's take that and change its limits. I just want to zoom in to make sure that it's starting out in the right spot. plt.xlim. Let's go bottom equals -1. How do I get that there? It had a left and a right. Oh, excuse me. That's going to be xlim. That's going to be ylim. Okay, yeah, it is starting out. I've zoomed in on that little hair at the beginning. It is starting out above there, but it's never coming back to that point. So that just above the y equals 0, right, at x equals 0 there. So this up here has a little curly Q up that shows my initial position. It has not come back to that. I would have to let it run for longer. Okay, well, that is very interesting. Might have to run that for longer in the future. In the meantime, thank you all so much for watching. I will see you next time. Bye-bye.